All right, so we're in section 13.5. So, when we talked about way back when we talked about single variable functions and we were learning to do derivatives, we had a chain rule. So that's just a quick recap. If we had y equals some f of x, and g is some, or sorry, x is some function of t equal g of t.
Y equals f of t?
I want y that is f of x, and then f is f of t. So I want them separate for now. We said when we use the chain rule, we said dy dt was dy dx, dx dt. That's our single variable chain rule. For multivariable functions, just like when we talked about second partial derivatives, because we can have various kinds of dependencies with our variables, we have several chain rules. So for the first one, I'm just going to call the first one case 1. So our first chain rule is where we have z, we have a multivariable function, z is f of x, y, and x and y are each a function of just one other variable. X is some function of t, and y is also a function of t. So z is indirectly a function of t. Just like up here, y is indirectly a function of t. Here, z is indirectly a function of t. And our assumption here, we're assuming that z, x, and y are differentiable. And because we're saying z is differentiable, that means our first partials are continuous. So our first partials are going to behave nicely. So we're going to say that for our case 1 chain rule is dz dt is dz dx dx dt plus dz dy dy dt. So that's our first chain rule. When we have a multivariable function and our variables x and y variables are only a function of one other variable. So basically just an expansion of this. Well, case 2 is when x and y are both functions of several other variables. So our case 2 chain rule is when we have z is a function of x and y, and x is a function of two other variables, g of s and t, and y is a function of s and t also. So we have some other things to consider here. So what we want to find the partial of z with respect to s and the partial of z with respect to t. And we have these intermediate variables that we have to deal with. So what we do here is we apply case 1 to each partial. So for the partial with respect to s, we're considering t a constant, and we apply case 1. For the partial with respect to t, we consider s a constant, and we apply case 1 to that partial derivative. So we're just splitting them up into two possibilities. So we get dz ds is going to be dz dx, and then the partial of x with respect to s plus the partial of z with respect to y times dy, the partial of y with respect to s. And then the same thing for our partial with respect to t. dz dt is going to be dz dx times dx dt plus dz dy times the partial of y with respect to t. So we apply this case 1 to each of these separately. And one way we can remember this is not particularly complicated, but we can draw a little visual for how this works. If we have, you can use a tree diagram. So we have z up here on top, and I'm going to say z is, for this particular diagram, z is a function of x and y. So there are two variables. So along this chain we do, or along this branch of the tree we do dz dx. Along this branch of the tree we do dz dy. And then if these two are functions of other variables, then we go along our other branches of our tree. So this would be the partial of x with respect to s, partial of x with respect to t, same thing for y. We call z, so this is just a kind of a visual way of looking at what we did there. We call z the independent variable. Just like anytime we're talking about functions, this is our independent variable. X and y are our intermediate variables. And then our s and t are our independent variables. And on this last step, if we only have one independent variable, then rather than a partial derivative, we would just have a normal derivative. So if we just had x as a function of t, we wouldn't take the partial of x with respect to t, we'd just take the derivative of x with respect to t. When we use a chain rule, we always want to express our answer in terms of the independent variables. So as when we use a chain rule, as part of it, we'll get dz dx and dz dy. So those will be derivatives with respect to x and y. So that will be in our answer. We'll do a couple of examples in just a minute. But we always want our answer in terms of the independent variables. So at the end, we need to substitute everything back in and get our answers in terms of the independent variables. And we can extend this idea of the chain rule, of the cases in our tree diagram for the chain rule, to if we have a function of any number of variables, where the intermediate variables are also a function of various other numbers of variables, and we just expand our tree diagram. We get more terms in our partial derivatives, that, but we just follow the exact same pattern. So in general, our pattern extends if z is a function. If we have w is a function of x, y, and z, so we had a 3-variable function, and x, y, and z are functions of 3 other independent variables. We would have just more terms in our partial derivative chain rule. We just extend the idea.
Wait, so Z and S and T are both independent?
Z is independent. Sorry, Z. Did I do it? Yeah, I said it backwards. Z is the dependent variable.
Okay.
Z is the dependent variable. Z depends on the other ones.
All right.
Thank you. If Z is the independent variable, then our function is nice and easy, right? So if we have more variables, various other kinds of dependencies, we just expand our tree diagram. We expand our list of partial derivatives to get our chain rule. All right, so let's look at an example of finding a derivative using a chain rule, and then I want to talk about implicit differentiation, how we can use the chain rule to help us simplify implicit differentiation. So any questions on our idea here of using chain rule? Okay. So let's say, for our example, we have w equals y to the third minus 3x squared y. X equals e to the s. Y equals e to the t. And we want our partial with respect to s, a partial with respect to t, and we want to evaluate at s equals 0 and t equals 1. So we want our partial derivatives, and then we want to evaluate them at these values of our independent variables. So if we wanted to, how could we do this problem without using chain rules? Just substitute in x and y, and then we'd have our function of expressed in terms of s and t, and then we could just find our partial derivatives. So, but we want to practice using the chain rule, so we can always just substitute in and find our derivatives that way. But we want to practice using the chain rule. So dw ds, the partial of w with respect to s, by our chain rule is going to be dw dx ds plus dw dy ds, and the partial of w with respect to t is going to be dw dx dt plus dw dy partial of y with respect to t. So we need to calculate our partials. We'll need our partial with respect to x and partial with respect to y of w for both of these, and then we need our partials of x and y with respect to s and t. So our partial of w with respect to x, what do we get? What do we get out of there for partial of w with respect to x? Let's see, that's a constant, and we get, what do we get? Minus 6xy. And our partial of w with respect to y, we get from this one 3y squared minus 3x squared. And then our partial of x with respect to s is e to the s. partial of x with respect to t is 0. That's kind of nice. dy ds, partial of y with respect to s, is 0. Another one kind of nice. And the partial of y with respect to t is e to the t. And now we're ready to substitute. We have everything we need to substitute. So our partial of w with respect to s is dw dx minus 6 xy times dx ds times e to the s plus the partial of w with respect to y, 3x squared y times dy ds, which is 0. So I just have that. And our partial of w with respect to t, I have dw dx times dx dt, 0, so that term falls out. And then the partial of w with respect to y times dy dt, so 3y squared minus 3x squared times e to the t. And this is where I said at the end we want to express our partials in terms of our independent variables. So we want our partials expressed in terms of x and t. So this is going to be, I'm going to substitute for x and y. So this is going to be minus 6 e to the s. Y is e to the t. E to the t times e to the s, so we get minus 6 e to the 2s e to the t. And we could also write that as minus 6 e to the 2s plus t. So that would be our partial expressed in terms of the independent variable. And then if we want to evaluate it at s equals 0, t equals 1, we substitute in I substitute 0 for s and 1 for t, and I get minus 6e. And then we want to express this, our partial with respect to t, in terms of our independent variable. So I'm going to substitute in there. I get, I'm going to put my e to the t out front here. E to the t times 3y squared. So 3e to the 2t minus 3x squared minus 3e to the 2s. And I could factor this, do some other simplification. This is fine. So this is my partial with respect to, of w with respect to t. And then I substitute at s equals 0. T equals 1. My partial becomes the partial of w with respect to t. I get 3e to the e squared minus 1. So I've factored out my e's, or n e. So that would be my partial evaluated at those values of the independent variable. And I would get the exact same result if I substituted for x and y first and took my partial with respect to x and my partial with respect to y. So questions on the process there. Just derivatives over and over again. Nothing particularly complicated. All right. Let's look at implicit differentiation, how we can simplify implicit differentiation with partial derivatives. So let's remember before we go on. Let's remember what when we're talking about implicit differentiation, what are we talking about? When would we do implicit differentiation? When would we need to do that? Do we remember? So when we have other things going on, so I'm thinking of something like x squared plus 2xy plus 2xy squared plus y squared equals 3. And we wanted to find dy dx. That would be an example of when we had to use implicit differentiation. Because y is a function of x, but it's not, the way it's expressed here, it's not explicit. We don't have y equals something. And it would be very difficult to solve for y in terms of x here. So this would be an example of something we would use implicit differentiation. Well, we can simplify the process. If you remember back to when we would do implicit differentiation, you would take all of your derivatives, and then you have to isolate dy dx. You find your derivatives and isolate dy dx. That's how we did implicit differentiation. But partial derivatives and our chain rule simplifies this. So let's say we have f of xy. I'm going to use a capital F here. F of xy equals 0. I could subtract 3 from both sides here, and I would get f of xy equals 0. I'd get this long function equal to 0. And we assume that y is a function of x. So we're going to say that this y is an implicit function of x. We don't have it written out as y equals f of x. We're going to assume that y is f of x implicitly. So I can say f of x equals 0. And I'm going to apply case 1 of the chain rule. I'm going to apply the chain rule to f. So I'm going to take the derivative of both sides. So I'm going to say df dx times dx dx plus the partial of f with respect to y dy dx equals 0 if I take the derivative with respect to x. Well, what is dx dx? 1. So I get the partial of f with respect to x plus the partial of f with respect to y times dy dx equals 0. And I can solve this for dy dx. Equals the negative partial of f with respect to x over the partial of f with respect to y. And we usually write this as negative f sub x over f sub y. And we want the partial of with respect to y not equal 0. So if we can write our function in the form f of xy equals 0, we can use partial derivatives and simplify implicit differentiation. So if you think back on how you would have to differentiate this implicitly, we'd take the derivative with respect to x, we'd have to use the product rule here, and everywhere we had a y, we'd also have a term dy dx. So our derivative with here would be 2y dy dx. here we get a 2i dy dx again. And we'd isolate dy dx. Well, here, we take the partial of f with respect to x, partial of f with respect to y, form this quotient, put a negative sign in front of it, and we're done. Kind of nice. Got a nice application of the chain rule, partial multivariable chain rule. And we can do a similar thing if we have more variables. So questions here on what we did. So dy dx is minus partial of f with respect to x over the partial of f with respect to y. If we have if our function capital F is a function of x, y, and z, and that equals 0, and we say that z is implicitly a function of x and y, we can apply the same process to f here that we just did when we had f is just a function of x and y. And we can get our partials of z with respect to x and y. dz dx is minus partial of f with respect to x over the partial of f with respect to z, and the partial of z with respect to y is minus partial of f with respect to y over f, partial of f with respect to z, and we're saying that the partial of f with respect to z is not equal to 0. And we could extend this for a function for as many variables as we want, and we could find the partials of our function with respect to the other variables using the same process. So we can expand this idea of implicit differentiation for a function of as many variables as we want. Questions there? All right, let's look at an example of using implicit differentiation, and then I want to talk about a application problem with partial derivatives. So let's say we have e to the xz plus xy equals 0. And we want the first partials of z. So here z is implicitly a function of x and y. So when we want the first partials of z, we want dz dx and dz dy. So finding dz dx and dz dy using the process that we've used before could be a little tedious. It could be hard work. Well, we have f of x, y, z equal to 0. So dz dx is just going to be minus f sub x over f sub z, and dz dy is just going to be minus f sub y over f sub z. That makes this nice and easy. So our partial f sub x. So this e to the xz plus xy is our capital F. So the partial of this with respect to x is going to be z e to the xz plus y. Partial of f with respect to y is going to be x, and the partial of f with respect to z is going to be x e to the xz. And now I'm set. I just substitute these values in. So it is e dx is minus z e to the xz plus y over x e to the xz. And dz dy minus partial with respect to y, x over x e to the xz. I can simplify that. Minus e to the minus xz. Much easier than trying to do it the other way that we've done in the past. Streamlines this process of implicit differentiation. And if we start off with our function not in the form f of x, y, z equals 0, we just rearrange it so we do get f of x, y, z equal to 0. Questions there? All right, so for the first part of chapter 13, what we're doing is kind of developing our toolbox, and then starting on Thursday, we're going to take those tools, partial derivatives, chain rules, the idea of limits, the idea of continuity. We're going to take those and we're going to actually start applying them. And we also talked about the idea of surfaces. Z equals f of x, y as a surface, our level curves, our contour lines. We're going to start taking those tools and applying them to doing things with multivariable functions, finding maximum and minimum, finding tangent planes, finding normal lines. These other applications that we're going to need to do throughout the rest of the semester. So we're still kind of building our toolbox with multivariable functions. We'll start using those tools to do other kinds of things in the next couple of weeks. All right, I wanted to do one application problem that involves a chain rule. So any questions on chain rule and implicit differentiation? Okay. So let's look at this problem. Here's my setup. I have this triangle. I'm going to call this angle theta, and this is a nice isosceles triangle. And we're going to say that x is increasing at 1/2 meter per hour, and theta is increasing at pi over 90 radians per hour. And what we want to do is find the rate of increase of the area. When x equals 6 and theta is pi over 4. So we want the rate of change of the area with respect to time. X and theta are both functions of time. So we have our area depending on x and theta, and x and theta both depend on time, so we're going to be using a chain rule. So we need dA dt. So using our chain rule, we know that dA dt is going to be the partial of a with respect to x times dx dt plus a partial of a with respect to theta times d theta dt. So that's what we're going to need to find. We need to find an expression. We need to come up with an expression for the area of this triangle in terms of x and theta. Let me draw another picture over here. So how do we find the area of a triangle? 1/2 base times height. So let me draw in a height here, an altitude. So this angle is going to be theta over 2. This is x, this is h, and I'm going to call this this piece the base divided by 2. So we said a equals 1/2 base times height. So we need to express our base and our height in terms of x and theta. So in terms of x and theta, how can we write our base and height in terms of x and theta? Well, don't we have a nice right triangle here? Yeah, so we can use some trigonometry. So our height in terms of x and theta. H equals x cosine theta over 2. And here's 1/2 the base. So 1/2 the base is going to be x sine theta over 2. So our area is x squared sine theta over 2 cosine theta over 2. Does this quantity sine theta over 2 cosine theta over 2 look familiar to anyone? Sine theta over 2. Because sine 2 theta is sine theta 2 sine theta cosine theta. So this is x squared over 2 sine theta. I'm using the identity sine 2 theta is 2 sine theta cosine theta. All right, so now we know that our area equals x squared over 2 sine theta, and we're all set. We're all set. Now we just need to substitute in. We can take our partial derivatives with respect to x and with respect to theta. We know that dx dt is, it tells us up here, 1/2 meter per hour. The theta dt is pi over 90 radians per hour. And we have our area expressed in terms of x and theta. So, rate of change of our area with respect to time. The partial of our area with respect to x is going to be x sine theta times dx dt, which is 1/2, plus partial of our area with respect to theta. So we get x squared over 2 cosine theta times d theta dt, pi over 90. And we want to calculate this when x is 6 and theta equals pi over 4. So we substitute in, calculate, and we get dA dt is approximately, when I plug these in, 2.566 square meters per hour. I like that problem. This is one where I had one student last year whenever we had problems like this, and we went from calculus to using trigonometry or geometry. Let's say. So how are we going to solve this problem? Let's say use geometry. That's kind of what we did. A little bit, kind of what we did here. We went back to here and found it. All right, questions on that problem? Okay. That's all I had for today. So our homework. There we go.